So last time I introduced the finite network effective resistance between B0 and B1, which is inverse of flux of B0. So the current flowing from B0 to B1. But now I want to recall some basic definitions. For example, you know from high school that divergence is just, for example, if we have a vector of Vx and Vy or Vz, and now we have two-dimensional vector, then the divergence of that is just partial derivative with respect to x plus partial derivative of the second entry with respect to y. And the divergence has a very important meaning in fluid mechanics, in many different areas of physics, in electromagnetics, that the divergence of I of x is just the sum of the current going out. For example, if x is adjacent to y. So if x is here and the current's going out, for example, this one, so if you sum over this becomes divergence of I of x. And the other thing that I need to just recall is about what is flux. You know that flux is defined as the sum over all of these divergences. So now we are summing over a set A, and so we have a set A, and if you sum the divergence from each of these points inside the sets, and some of them are connected, then this is the flux. We call it the flux of I B0. Flux of IA here, for example. And these are enough to just declare a very important theorem and then proving it. The theorem says that if B0 is just a subset of A and A is just a subset of V as usual, so we have some vertex X inside B0, so this is B0, and here is just A, so between them is just A minus B0, and also we have another set B1, so all of them are just a subset of your vertices of your graph. So imagine this picture in your mind for several reasons. So imagine this for many reasons. So the theorem says that if B0 is inside A and it is inside V with A is finite, then we want to prove that if we sum over all points inside B0, the sum of probabilities that tau A is less than time to return to B0, if you multiply it by mu x, is just the reverse of the finite network effective resistance of finite network of B0 and V minus A. And also we want to prove that the effective resistance, finite network effective resistance of X0 and V minus A is just equal to GA X0 and X0. So let's say that this we want to prove this one and this one. So how do we prove that? We first imagine again that D is just this set and B1 is V minus A, and just define the function phi of x that we love to define like this. And now you know that I is just the gradient of phi, and for any x in B0, so we can say that phi of x is 0. And divergence of I of x is just the sum over phi of y minus phi of x is 0. So I put just 0 here and times mu x mu y. So I've just written the definition of divergence of I of x, and because phi has such a value which is 0, so we can write this as, and the summation is as usual over y. And this is equal to, as you see, just by definition, we write it as this. And then this is the probability that the time to B1, time to hit B1 is less than time to hit B0. And this is equal to, we can say it is equal to the probability that TB1 is less than TB0. So we have shown you this technique for several times. So the proof of the first part follows just from the definition of effective resistance. But for the second part, which we want to prove that I told you the effective resistance of x0 and v minus a is just equal to GA x0 and x0. So to prove that, we just take your set to be singleton, just one atom. And we just deduce that the probability that if we start from x0 and time tau a is just less than time to return to that point, times mu x0 is just inverse of effective resistance of x0 and v minus a. So we just compare it with this that we know is mu x0 tau a is less than equal to return to x0, and so we prove this one. So the proof was very simple. And now we want to talk about effective conductance between B0 and B1, which is by definition the infimum of that Dirichlet energy that I told you 2 lectures ago for all functions inside this function space. Remember that this function space is just by definition all functions that is finite energy, and also f restricted to B1 is 1, f restricted to B0 is 0. Now I want to prove the theorem that says that if this conductance between two sets is finite, so if the conductance between two sets is finite, then F is the solution of the Dirichlet energy. So F of x is 0 and B0 and B1 is 1. And also the Laplacian, it satisfies the Laplacian and V minus B0 union B1. So imagine we have some vertices of the graph. We have x0, we have B0, we have B1. And just observe that, so to prove that, just observe that F satisfies the boundary condition. And just let x to be this point, which is V minus B0 and B1. And just let h of y to be 1 of y. So it's indicator function. Then for any lambda in R, the function f plus lambda h is in that function space that I told you. And here, in order to continue this proof, we need a simple theorem that says that if H is a Hilbert space and A is a subset of that, and but A is just a closed, non-empty convex subset, then there exists a unique element in your Hilbert space with minimal norm. And also, if H is just a function in this Hilbert space, then there exists some delta such that G plus lambda H is in A for any lambda less than delta. And then we conclude that H and G, the inner product of them is 0. And now we want to use this property that the inner product of them is 0. So we can conclude that the energy between F and H is 0 because H is in the function space of V. And 0 is the energy between F and H, and by definition is just delta F and H and mu x delta F. So we conclude that because this is equal to 0, we conclude that your F function is harmonic in this space, V minus B0 union B1. So we have proved this theorem. And another important lemma is, so we have two more lemmas before we get into the Carnot-Varepalus bound, which is very important for me. And even Yuval Perez has said the importance of Carnot-Varepalus bound in his book. Also, many mathematicians have been interested in that, and I will tell you why they are interested in that theorem. But before that, I just want to show you a lemma which is related to effective resistance. Just the lemma says that I want to just to declare that the effective resistance of X and A, if you inverse of that minus the probability that Tx star is Ta is less than equal to the probability that return to X greater than Ta is bounded by mu x effective resistance. Another important theorem, another important lemma that I want to talk is that if X is not in A union B, so if the probability that Ta union of B is less than infinity, if this probability is 1, then we conclude that the time to hit A, if time to hit A is less than time to hit B, if the probability of this event happens, is bounded by just a fraction of effective resistances. So you see, effective resistance is playing an important role in identifying and calculating all of these probabilities. And also this is bounded by X and B, and this is bounded by X and A. So to prove this, we say that what is the probability that time to hit A is less than time to hit B? We just condition on another event. So we say that Ta could be less than Tb, and Ta. So there are two conditions for this. Either Tab is less than T return to X, or the same thing, Ta is less than Tb, but now this time Ta union B is greater than Tx. And just by Markov property, I can say that the second term if you apply the Markov property at Tx plus, then this term becomes Ta less than Tb. The probability that Ta union B is greater than time to return to X. So we can conclude that the probability that if we start from X, time to hit A is less than time to hit B, the probability of this event is equal to, so we have simplified it to saying that this is just the probability that Ta is less than Tb and Ta union B is less than return to X. And this is the probability of Ta union B less than Tx plus. And this is just bounded by the probability that Ta is less than Tx plus. And it is bounded by Ta union B less than Tx plus. So using the previous lemma, we just give you an upper bound. And now I want to start about the Carne-Varapoulos bound. This Indian mathematicians, Greek mathematician, Varapoulos, and so the reason that this bound is very important, as mentioned by Yuval Perez and many other mathematicians, is that there is a way to, in the proof of this, we understand that how to relate the probability of X and Y. So if you start from X time to hit after n time steps, we reach Y, and this is the transition probability on the graph, on the weighted graph. We relate it to a random walk on ZD, let's say. Of course, we just need to use it for D equal to 1 in the proof of this. And this is very interesting result because you have related a very complicated object to a simple object like random walk on ZD, which we are very familiar with that. We can create beautiful measures in that. We understand it. There are several books written on this. So this side is very simple. But this side is very mysterious because a random walk on a general weighted graph is very general. It could lead to anything, and we don't know how to do qualitative analysis of that. So we are trying to use a trick to use a dual of that dual process. So it is even more than the coupling approach that you use a dual random variable. Here we are using a dual process. The process could be even completely different from the primary process. And by analyzing the dual process, we can understand about this one. For this idea the meta idea is very general. For example, you want to find the function space, you do Fourier transform, and in the frequency domain you understand those functions easier. So you have seen this in several parts of mathematics, and we call it this is the dual space, for example, the Fourier space, and this is the primary space of functions. So by doing that, we are just trying to work on a very simple and interesting domain rather than very crazy and complicated space. So this is the trick that is so interesting that I cannot go to bed at nights, because when I think about it, I see that